Hi, my name is Eamon, and today I will be presenting heap sort. Now, as we've already learned, heaps are a data structure that allow us to give elements a certain ordering based on their priority. So we can either have a min heap with the smallest element at the top, or a max heap with the largest element at the top. Now, using this, one might wonder, is there a way to retrieve our elements in sorted order by continuously removing them? And there actually is. This is called heap sort. Now, heap sort occurs in two main steps. The first is taking a random array, how do we heapify it? And the second is, once we have our heap, how do we sort it? Now we'll start with the second part since it's a bit simpler. Now, here we have our min heap, and we want to continuously remove our minimum element. So in this case, we'd be removing 1, and to preserve the shape invariant of our heap, we'd replace 6 with 1, place it at the 0 index, and put 1 at the very end of our array. This would yield us the following heap with 1 removed, with 6 at the very top, 4, 2, and 7 in their original places. Now, clearly for this heap, the order invariant is no longer preserved, since 6 is larger than both 4 and 2. So to fix that, we need to bubble down 6 with the smaller of its two children, which is 2, and that yields us the following heap. This heap has the following array representation. And since we swapped 1 with 6, 1 is placed at the very end of the array. And we can split this array into two main portions, the heap portion and the sorted portion. And so what we're going to continuously do is bubble this boundary forward, swapping our minimum element with the last element in our heap, and getting our elements in descending order. So if we repeat it multiple times, we'll get the following array. One thing to note is this operation only needs to be performed n-1 times, since the very last element in our heap is always going to be either our very smallest element or our very largest element, such as 7 here. And since we know that the time complexity of removing an element from a heap is O of log n, since we need to preserve the order invariant each time, we know that the total time complexity of our sorting operation is O of n log n. Now, an interesting thing to note here is that a min heap actually returns our elements in descending order, starting from largest to smallest. And this makes sense because we're placing the very smallest element at the very end of the array. And consequently, a max heap will give our elements in ascending order. Now, since we're assuming that our array is a heap from the very beginning, one might wonder, how do we get to a heap from just a random array? And the way to do this is through heapifying. Now, an array will always have the shape invariant of a heap preserved, since all the elements are going to be filled, which is what we're assuming. So what we really need to fix here is the order invariant of our array. And we can do this by looking from the very bottom, subtree by subtree, until we encompass the whole binary tree. So if we start looking at 4 is a perfectly valid min heap. Since 4 is the smallest element of its respective subtree, it has no children. We can also look at 2. 2 is a perfectly valid min heap since it also has no children and there's nowhere to bubble it down. If we look at 7 is just by itself, so it's a perfectly valid min heap. Then we can look at 1. Now 1 actually has children, so we need to check if its children are smaller than it. In this case, they are, so we don't need to bubble anything down. And finally, we can look at 6. 6 no longer preserves the order invariance. It's larger than 1, so it needs to be bubbled down. It's larger than 1, and it's also larger than 2, and that yields us the following min heap. Now, since we only need to check nodes that have children, we can actually skip over all the leaves in our array. So we can start by checking at the n-1th element over 2, and then bubble down elements if they are larger than their children. Now, the math behind this is a bit subtle, but it turns out this operation has O of n complexity. Now this is strictly smaller than O of n log n. So our operation has a total complexity of O of n log n. It's dominated by the sorting portion. And to remind you, the min heap will give us our elements in descending order, while a max heap will give our elements in ascending order. And that can be resolved in the heapifying portion. We can either bubble the largest element down or the smallest element down based on what we want. Thank you for listening.